So it's my pleasure to have with us Cedric. He is a rover lead avionics engineer at Astrobotics. Astrobotics is a 10-year-old company out of Pittsburgh, which has been doing some phenomenal work with NASA. And he's going to talk about some of this work on Cube rovers. But just to talk a little bit about Cedric, Cedric has expertise across multiple domains: robotics, signal processing, embedded software, avionic design, and he's also the PI lead for the Cube Rover Tipping Point program, which is the focus is to develop an industry solution for lightweight mobile robotic platforms for lunar mission. He also has collaborations with Josh here on wireless charging of some of these lunar surface missions. So really exciting work at the forefront of space exploration and moon exploration, even better. So with that, the floor is yours, Cedric.
Thank you very much, and thanks again for having me today. It's an absolute pleasure to present what we do at Astrobotic. And please, if you have any question, feel free to interrupt me. I'm happy to answer any question you have. I would like to be more like conversation than just a one-way presentation. So feel free to ask any question at any time. Yeah, my name is Cedric. I've joined Astrobotic, it's been now a year and a half. I'm working on the planetary mobility department, and my job is to design the electronics of the rover, the Cube rover. So it's a small rover that is designed to operate on the surface of the moon. Currently, our goal is to design a rover that can survive a lunar day, so which is 14 days. And yeah, you keep me busy quite a bit. So why the moon? So I'm not sure if you heard or not, but there is a lot of interest from NASA to send people to the moon. So and there's a program called Artemis. So essentially, the goal of NASA is to have a permanent presence of the men and women on the surface of the moon, and to essentially enable future exploration. So why the moon? So on the moon there is a huge amount of fuel actually that could be used to power rockets to go to Mars. The idea of using the moon to go to Mars is essentially because it's very expensive to launch big rockets that carry enough fuel to go to Mars. The idea would be to use the moon as a fuel stop, essentially, where we would extract the hydrogen stuck under the surface of the moon with robots, essentially. So you can see a couple picture on the left here, where we would process the lunar dust, extract the hydrogen, and with hydrogen, as you know, we can make fuel with that. So that require a pretty big infrastructure, to support those type of things. So you need the power infrastructure, you need the robots, but you also need the habitat and the protection for the astronauts to support those type of operation there. So definitely, an exploration interest. So the moon will enable the humankind to go further, but also there is definitely some scientific needs. We need to better understand the moon. Even if we can see every night, there is a lot of mysterious things that are happening on the moon, not only on the surface, but what's going on under the surface and at its core as well. So there is a lot of things that are not well known on the moon. So for instance, on the top right, you can see a little illustration here. It's an actual a pit that is supposedly was created at the time where the moon was more active, and currently, NASA thinks that there is a network of those pits that could bring 2 tunnels under the surface of the moon. Those pits could be, very, very interesting, to better understand the geology of the moon, but also could be also a place for, for a permanent bases to locate themselves, where they are protected, they are under the surface, protected from asteroids and radiation as well. So there is a lot of interest in exploring those type of areas on the moon. You can imagine before we send astronauts to those pits, we want to send robots first, so rovers or maybe even little aircraft, spacecraft, I should say, that could navigate in those pits. And there is a need, and a lot of interest to do mapping of those areas to understand how they look inside. And yeah, so that's an area of interest here, to explore the moon and better understand its geology, and yeah. Also, yeah, study how how life could happen on other planetary bodies other than Earth. I think there is a lot of interesting challenge to solve there, and that could be, it would prepare us to go to Mars down the line. So having a foothold on the moon would give a good exercise for the astronauts to live on Mars. And yeah, and the multi-planet species, that would be humankind will be the only species, what I know, and most people know on Earth, that we would be a species that live on multiple planets. So yeah, so there is definitely a lot of interest to go to the moon, and just to better understand, the solar system and beyond. So so Astrobody currently its main focus is the moon, but down the line we may go to other planetary bodies, but there is a lot of work already just to get to the moon. So just to give you a quick highlight of the program we work on at Astrobody. So we have 2 landers currently. So we have the Peregrine landers, and the Peregrine lander and the Griffin lander. The Peregrine lander is designed to carry multiple type of payloads from NASA or universities or research labs. So the design of that lander is really to, I don't know if you can see, but there is another picture later in the presentation, but there is decks here on the lander where you can actually mount your payloads, and essentially the scientific the science person will design his payload, and we will take care of bringing it to the moon, landing safely, and relay the data, and we would relay the science data to Earth and give it to our partners and customer to process the data. We also have a Griffin lander, which is bigger. This one can carry 500 kilogram payloads. And this one actually will fly the Viper rover in 2023 to the South Pole of the moon to find water. So you can see here it has some ramps on the side here, on each side, where the rover will be sitting on top, and it will land. And once the rover is ready to deploy, the ramp will just unfold, and the rover will drive down the lander here. We also work on rovers. So Cube rover is a rover I'm currently working on. We are working on 3 sizes of rovers. So the one you see in the picture is the smallest size rover. It's a 2U Cube rover. So I don't know if you're familiar with the CubeSat platform, but essentially CubeSat is a satellite platform that is designed to carry predefined payload size, or payload volume, I should say, where 1U represents a 10 centimeter cube size essentially. So a 2U cube rover would let you bring 20 centimeter by 10 by 10 essentially volume of payload on the rover, and that platform will be scalable, or is scalable, and we have a 4U cube rover and a 6U cube rover as well. And those really are designed to carry, payload beyond just the landing site. There is some interest from the community to, explore beyond where you just land. Well, landing is already a big thing, but exploring further where you, if you want to scan the surface or to understand, for instance, I don't know, the electric field of the surface of the moon, for instance, or the effect of the, of the lunar dust on, I don't know, on radio, for instance. There is a lot of interest there to scan the surface of the moon to understand how, in preparation of those future missions, essentially, collect all those data. We also have the Polaris rover. So this one is a much bigger rover. I don't know if the picture gives much credit, but the the Polaris rover is about the size of a golf cart, essentially, and the Cube rover is about the size of a big shoebox, essentially, maybe a moving box for one of the biggest ones. So yeah, so but the picture doesn't give very much credit there, but yeah, just to give you an idea of scale. And you can see currently both designs of those rovers are designed to work on at the pole of the moon. So that's why they have their solar panel oriented vertically, because the sun is right above the horizon. And also, what we work on is, I don't show it in that slide deck, but currently we started to work on the wireless charging system with Josh to support wireless charging of rovers. Essentially, there is some instance where the lunar dust is pretty messy when you start to scramble with it, essentially. It sticks to everywhere. It's very bad for rovers and for any moving joint, essentially, or solar panel. And a way to mitigate that would be to remove the solar panel and replace them with some wireless charging, where the rover will drive away from the lander, do its operation, and when he needs to recharge his battery, he drives back to the lander to a charging station and will recharge its battery wirelessly. So we work in partner with Wybotic on that project, and our goal is to flight qualify the system. So I can tell you more about what flight qualification means in terms of engineering later in the presentation, but it presents very interesting challenges, very interesting engineering challenges to general design. At Astrobotic, we also work on we have a department called Future Missions and Technology. So that department is working more on preparing the future of the company. So we work on precision landing, on mission simulation. We also work on making some navigation autonomy for rovers, and also supporting space computing. So the precision landing actually will be demonstrated in our next flight to the moon, where it is very important to know where we are going to, well, to have the lander be capable of landing in a safe zone, because there is a lot of craters and rocks on the moon, and because we carry so many payloads, we want to make sure that we land safely. And the software and hardware we developed essentially will make sure that it takes over the flight control of the lander. So we have a camera looking at the ground, and essentially it will be able to detect obstacle and pilot the lander and the final phase of this descent to land it in a safe location. So it's a really cool software, and I think maybe I have a little video later to show how it works. But yeah, really cool software and hardware running on that. As you can imagine, in order to support those and test that, we need to simulate. So we do some work in rendering the lunar surface. So you can see here on the little picture here, it's actually a rendered version of the moon, surface of the moon. So you can set a time and a location, and essentially it will recreate the surface of the moon for a given time and location here. And we exercise our hardware against those to make sure that we have a robust design. Autonomous hardware, yeah, we do work on LiDAR and drone work, so mapping indoor areas the same way, just for if it's a drone, to avoid to touch the wall of a cavern, for instance, or fly down a pit, for instance. So we do those type of works as well. And lastly, we do some work in space computing. So we work on creating hardware that can be flight qualified and present all the robust aspect of the design aspect of good thermal management and radiation protection and all of that. Astronav, yeah. So
let me ask a question. How is the space computing future work different? I'm assuming that the rovers and other things which you're deployed today also need some computing. So what's the challenging part here?
Good question. We designed some hardware, essentially, that presents some redundancy in the design. So you have the option either to buy some hardware that exists that is already space qualified, but we also work on developing our own hardware that is very tailored to our needs. So it could be like redundant processing computing unit, it could be high performance, low power platform. So because we, especially for rovers, we are very limited in power. So we design some systems that essentially are low power, high efficiency computational capability.
Do you design your own ICs to do that? Or?
No, we don't go down to the IC, but we pick good processors, and we qualify the board that goes with it, and make sure that it's designed in such a way that it's at least for the rover low power, or as low as possible for the rover.
So it seems like a lot of interesting embedded systems work. Is there other issues other than low power, other issues in terms of errors and so on, which happen in the space?
Yes, good question. Yes, so you are exposed to various things in space. So you are exposed to thermal variation. When you are at the pole, depending if you are exposed to the sun radiation or in a shadow area, the temperature can vary between minus 200 Celsius to plus 150 Celsius. And when you are a small rover, those temperature can vary pretty quickly, because you have a small thermal mass. So you need to be aware of the component you pick. So you want to extend as much as possible your temperature range, your operating temperature range. So you need to have a good thermal management. But temperature is not the only thing. What could create some error is also the exposure to radiation. So two things you need to consider as far as radiation. You have the total dose you receive of radiation. So essentially, it would be essentially taking one X-ray is okay. Taking an X-ray per day for 2 years, it starts to be pretty bad for you. And it works essentially the same for electronics as well. So if they spend a few weeks in space, you could ignore that effect. But if the hardware is designed to spend several years, the performance of the electronics will start to degrade. So all the semiconductor, all the internal resistance will start to increase, for instance, and your performance will decrease over time. So the component will fatigue more than normal, and more quickly than normal. So that's the total ionization dose, or TID, that we need to look at. But also there is some effect called single event latch or upset. So those are triggered by heavy ion particles just hitting the circuit at random spot at random time. They come from the solar wind, or or the deep space essentially, and those could have an effect of flipping a bit, for instance, on your memory in your flash or your RAM. Or they could trigger the gate of a transistor, for instance. Or they could, by triggering those type of gates, for instance, they could put your microprocessor in a weird configuration where it's not designed to. And generally, you can take care of those in two ways. Either you add more shielding around your system, so you need to add more aluminum essentially, so you have a big box surrounding your avionics so it can absorb those particles. But a mass is expensive to ship to space. So a second option is to have radiation tolerant part, and those parts are generally way more expensive, but they are designed to be robust to those type of events. So that's another option. Or if you simply don't have a radiation tolerant for a specific processor you need to use, or some specific function of your circuit, you can monitor your circuit by at a system level, for instance. Generally, those events will manifest as either overcurrent or some current consumption that are not nominal, and you could detect that at a system level and, for instance, reset the device to fix the issue. Generally, those type of events could be mitigated by just power cycling the device. So let's say you could have a redundant processor working in parallel. Let's say one got impacted by these events, and the second one could continue to work normally, while the first one could work normally, while the second one would reset and catch up with the first one. So that's why you see redundant system in those type of critical design to mitigate those type of effects. Other effect to look into, for some sensitive components will be, vibration and shock. If you have some sensitive parts that live in your system, because they need to survive the launch, we need to test those as well, to vibration and shock. Vacuum also could be a pretty big factor, for optics, for instance, could be sensitive to vacuum condition. But yeah, it was a long answer. I'm sorry.
No, that was good. That's pretty good.
So yeah, so here is an illustration of Astronav. So that's we use SLAM essentially, and LiDAR, combination of them, inertial LiDAR and SLAM to map some pits. Yeah, here it's you can see it's a little picture of a spacecraft that could take off from the little Polaris rover we have on the surface and go inside and explore the pit, collect the data, and then fly back to the rover and upload its data and yeah, collect it back to Earth.
Are these manually navigated, or are they is the machine learning to navigate them automatically?
Those will be autonomous. Yeah, they are autonomous. The spacecraft is autonomous. The rover would be most likely, well, it depends on where you go, but it could be remotely controlled. So here it was some tests we did in New Mexico. So we have a little Excopter here with a LiDAR, with a processing unit, and a little wireless system too. I can see it has an IMU, and yeah, it flew down a pit and do mapping of the pit. So it was done before I worked for the company, but yeah, it's still at the office. Oh, here you can see, I don't know if the video is smooth or not, but you can see
It looks good, actually.
the system.
But on the moon, the flying device would use rockets, I suppose.
Yeah. Mm-hmm.
Is there a plan to put, that sort of thing on the moon, kind of like a drone, similar to what they're doing on Mars right now?
I would love to participate to that project. I'm not aware of a drone just yet. Like a NASA project that will schedule a flight for that. But yeah, I'm not sure if you can hear it. It's very loud. I'm not sure if you want the sound, but it's very loud in my headphones.
So you guys developed the SLAM algorithms yourself, or?
I believe so. Yeah, I believe. Yeah.
Very cool.
Yeah, those type of GPS denied application are really interesting for NASA. Definitely, there's quite a huge challenge there in robotics, even on Earth, to have robots drive on their own without any GPS data or way to correct their estimation and their position. So.
So speaking of GPS denied, I know there's a plan for like Nokia is deploying a cell phone network on the moon, right? Is there any plan for like a GPS on the moon?
So there is a project at NASA called LunaNet that would be like to set up a constellation of satellite around the moon. I don't know if I think the primary goal is to provide a telecommunication relay to surface asset, but I don't know if the goal is to get to reach the same accuracy that the GPS we have on Earth here. I'm not 100% sure. I'm sure, yes, I'm sure it could be used to do localization because there will be several satellites circulating around the lunar orbit, but I don't know yet any specs on as far as GPS.
I mean, here is a dumb question, but can you hear I mean, they're probably much weaker, but have people tried to hear the transmissions from the Earth GPS satellites on the moon, or is that just super weak that you can't hear them?
I think the beam is not in the right direction. I don't know. I think yeah, and you need to be you need 3 satellites, you know, to be able to triangulate the at least 3 to triangulate the position. So yeah, I don't think. I'm sure the same technology could work on the moon, you know, if you deploy the same type of satellite around the moon. But yeah. Here are more pictures. I don't think there is any videos here. Oh, here, yeah, we are also looking in other, you know, beyond the moon as well. So this mission, let's see, it was, where was it? It's here, just yeah. So yeah, so that was just beyond the moon. I didn't work on that project specifically, so I cannot comment too much on this one.
Do you guys publish papers at Astrobotic? Because some of these things I think would definitely be of interest. You know.
We do have white papers, not in my department, but I know the Future Mission and Technology has published some papers there. So yeah, here it's an illustration of the Terrain Relative Navigation, TRN. And actually that similar technology was used for the landing on Mars last week or 2 weeks ago. You can see that at some point, if you watch the video of the Perseverance landing, at some point you see the lander enabling the TRN. And that's at the point where essentially the computer on board take control of the flight command and to identify where to land. So essentially, yeah, the lander has a map on board that is used as a reference, and the lander try to recognize those spots as it progresses toward the surface. And it controls the speed, the velocity of the approach, and as it's getting closer, it gets more resolution and is capable of detecting rocks and essentially just do a precise landing. Here is a video of the TRN system.
Is that did you call that the Peregrine?
No, this was a test fixture to test our TRN system. This is not a Peregrine lander. There is a picture, I believe, later in the presentation to a better picture. Yep.
So we have a question from Asit, a little bit about testing and simulating the stuff. You showed videos of the drone flying around in that environment, which looks moon-like, and also like, how are you confident? What is the whole process of going from what you have to testing it out? How do you simulate the moon environment, for example, the radiation, the lack of gravity, and all those things?
Great question, and there is many answers to that. So I will try to cover them all. So to test the TRN here, so here you can see we tested with actual hardware. But in the previous slide, I was showing you that we developed a software to simulate the lunar surface. So we actually do a hardware in loop simulation where we feed the video to the hardware, and essentially, the hardware controls the software, and essentially, it's a hardware in loop simulation. So we do that to verify our TRN is working as it's supposed to. Radiation testing, we will go to test facilities to essentially accelerate. We will expose our electronics to radiation. So we'll go to a test facility to simulate that. We can do total dose radiation, and we can do simulation of latch as well. So the way the test is set up, typically you bring your PCB, your printed circuit board, to the test facility, and you say, I want to test that area of the circuit, and you put your device in, and it will just blast some ions to your circuit, and you monitor what's going on. So this is how we verify that the system is safe to use. To test vacuum and temperature variation, we have a thermal vacuum chamber at Astrobotic, where essentially before putting the actual hardware in the chamber, we have some simulation software that model the rover and any other hardware, but I will take the rover as example here. So we have a thermal simulation software that simulate the heat we will receive from the sun, the heat that is generated from the surface because of the sun reflecting on the dust and reflecting back on the rover. We can simulate how much heat we lose because of the lack of insulation, for instance. And because we know the material we're going to use, we know where we're going to put the insulation, we can simulate the thermal transient and thermal sorry. I want to say static, but it's sorry. Stable condition, essentially, equilibrium condition, essentially, where your system becomes stable. So we do all those simulations. So essentially, you can imagine the rover simulated as a mesh, where each intersection of the mesh represents a temperature point. So we do our simulation, and once we come up with a model of the rover, we will verify that model in our thermal chamber, vacuum chamber. So we will take our rover, or prototype rover, we will install a lot of thermistors or thermocouple, sorry. And we will apply the heat cycle in vacuum condition. And by looking at how the temperature varies, essentially we will be able to refine our model, or refine and verify our model. And if our model is correct, then it means that all the environmental conditions we simulated before will be also correct. So therefore, we can estimate what will be the behavior of the rover once it's on the surface of the moon. Does that make sense? Okay. Vibration. We also have a shake table at Astrobotic. So you can imagine it's a pretty big table with a big magnet, essentially, that can shake at whatever amplitude and frequency to essentially simulate launch conditions. So you can simulate shocks. They can also simulate sinusoidal excitement, all type of excitement that will be seen during the takeoff.
It seems like it's a bunch of, some of them are external companies you guys go and test it, and some of them are you have infrastructure within Astrobotics to test it out.
We do TVAC, so vacuum testing at Astrobotic. We also have the table at Astrobotic. So those tests are done internally. The radiation, yeah, because it involves nuclear material. We cannot do that at Astrobotic, but we have to go to very dedicated test facility to do that. So and yeah.
Another question, which probably you're going to cover later, is about Masato again, is about how do you keep the rover's battery at the right optimal operating condition as the temperature on the moon is very low? Do you have a custom heater to maintain the temperature?
Yeah, great question. We do, and I will cover maybe another point you mentioned earlier, the low gravity as well. So to test the low gravity, what we do, gravity is essentially important for our mobility testing for the rover, because we need to design wheels, we need to design the center of gravity of the rover need to be designed in such a way that it will work for lower gravity as well. So what we do, we have a test bed at Astrobotic, where we have a lunar dust simulant, regolith simulant, a test bed filled with that. And essentially we can do two things. Either we build a lighter rover that will be 1/6 of the mass of the actual rover, or we could offload the rover using, either helium, a big helium balloon, that will lighten the rover, or we could use a system of arm, essentially, and pulley to lift the rover to reduce its mass on Earth. So those are the options we could use to simulate low gravity. And I forgot your question.
It's about the battery temperature.
Oh, thank you. Yes, we do check carefully for that. Absolutely. So I will show you a picture of the rover in the upcoming slide, and maybe I can cover that point. So here is a closer view of our Peregrine lander. So you can see the deck here filled with payloads. I don't know if you can see my cursor, but essentially everything that is not part of the platform here is a payload we have from NASA, essentially. So here the vertical panels are actually radiator. So the radiators are used to cool the lander, because it can get very hot. And yeah, here the golden tanks here are or fuel or propellant, and below here you cannot clearly see, but essentially here you have your little the engines, essentially. And yeah. This is a rover also that will fly to the moon in 2022. We work in partnership with Carnegie Mellon University. So Moon Ranger is first of its kind, essentially. It is an autonomous rover, so we are going to demonstrate the technology that a rover can drive autonomously on the surface of the moon. So that rover will be deployed from a lander, drive away outside of the radio range, collect some. I believe it will collect some neutron data. It has a neutron spectrometer on board to collect quantities of the type of neutrons, I guess, that exist on the surface of the moon. And yeah, we collect some scientific data, and once it's done with this mission, it will drive back autonomously to the lander. So we will do that progressively, of course. We will drive away, engage the self-driving and within radio range, just to make sure the software is working well, and we will be a little bit more take a little bit more challenges, and drive further and further away from the lander just to verify the system. So yeah, that's an exciting project too. We'll fly next year. This is our mission 3 at Astrobotic. So that we fly on the Griffin lander. You can see the rover on top of it is a Viper rover. So this rover is designed by NASA and is designed to essentially drill the surface of the moon to find water at the pole. So that lander will land where NASA is really interested in putting the first permanent base on the moon. So at the South Pole. I don't know if the exact landing site is identified, but it is probably not public. But yeah, we're super excited to work with NASA to work on that project. Yeah, very cool rover, very cool lander there. So this rover will be teleoperated It won't be self-driving, but yeah, 2023. Yep. Yeah, this is just to give you the list of people we work with on our first mission. You have all type of background. We have a couple rovers there flying. We have personal Objective flying with us, through our DHL partnership. So we have the Moonbox. If you go on our website, we advertise for Moonbox. So if you want to ship something you would like to see on the moon, that's a service we can provide. Here it was, a couple updates on our progress. So we did some engine testing. We did our structural model, test model as well here. That's a model we have used to, we put on the shake table to make sure that we were not losing bolts and screws during the launch, but it was very good. We don't lose anything, so we're good there. We just moved to a new headquarters last summer, so very exciting place to work. We actually have a little museum area that opens to our clean room, so for the public to see when possible, the assembly of the lander, and we also have all the other prototype we have there. And you can see here, because we carry many payloads, and the payloads need to verify that they work properly with the lander. We have essentially a lander simulator, so it's a little box essentially that is used to simulate the interface, a communication interface to the lander, and that is being used for the payloads to work with us. This is our control room. So our control room is in Pittsburgh as well, in our Astrobotic office. So we will fly our lander from our office. So yeah, this is this is a preview of how it will look like this year, hopefully when our lander arrives on the moon. So we fly with ULA. This is another view of our landers. We have a couple antennas. We have our medium gain antenna designed there for the communication back to Earth, essentially. And we have also some local antennas that we support our rovers, for the short range. I mentioned the radiator. We have solar panels as well. The top. Yeah, here's to give you another view of where you can install rovers and payloads. So I mentioned before, but you have decks where you can bolt your payload on top, at the bottom. As a rover, we will be installed at the bottom deck, where we get deployed, drop from the deck, and drop on the surface and drive away, essentially. Just to give you a sense of the cost, what it costs to bring a kilogram of material to the surface of the moon. That's about the cost you look at, between engineering, fly, all the logistics that goes around it, that end up being that. So I mentioned earlier, one way to mitigate radiation is to add more metal around your avionics. At that cost, you think twice, if you want a 3 millimeter thick aluminum cage or 2 millimeter thick enclosure. So every gram you spend has a direct cost on your mission. So that's a very interesting approach you take when you design and engineering challenges. It's not necessarily every day you need to think that way when you design a piece of hardware that needs to be controlled very tightly on the mass. Let's see. A couple comments here as well on the surface hops. So the lander is designed to survive a lunar day, and because it is pretty challenging to survive the night because you need to keep the lander warm during the night. So you need to bring enough batteries to keep the system warm to protect the batteries. So that answered a little bit your question you had before. And also all the electronics. Currently, our lander cannot support that because that's a lot of you need to bring a lot of batteries to keep the lander warm during 12 days and minus 200 degrees Celsius. So currently our lander just survived 12 days, just the lunar day. This is their communication bandwidth we offer, power and areas essentially you can work with. Let's see. Oh, this is to show the type of orbits we support. So before we actually reach the moon, we can drop some payloads on our way there as well. So you can see here, it's a little satellite here. So before we actually reach the moon, we have 3 orbits, LO1, LO2, and LO3. If our payload customer want to follow that orbits, for instance, they can decide to be deployed at the right time, and they will follow that orbit. And the closest one would be LO3 here. So the deck could be activated anytime during the flight to launch some kind of satellite as well before it actually lands. This is there's a little bit more recent picture of our rover, but this is where it was standing about 6 months ago. This is our design. This is pretty close form factor wise of how it looks today.
Quick question: what do you mean by 10 kilobit per second per kilogram? Like, why does kilogram affect the payload I mean, thought that you have an antenna, a communication length. So why does it depend on the weight?
Good question. Because we have a very limited bandwidth between the lander and Earth, and this because you pay per kilogram for your flight, we also give we give a chunk of bandwidth that goes with that pricing. And the bigger you are, if you need it, the more you could have more bandwidth essentially. So it's a ride share, on the lander side, and that's how we manage it essentially. But there is a lot of case by case. We need to see, so on average, I think it's an average bandwidth that we allowed. And we advertise the same for rover. Essentially, we follow the same type of model. But yeah, here it's a view of our Cube rover. The top section of the kind of aluminum chassis you can see here at the top, this is where all the batteries and avionics goes essentially. So it's a very slim interface. And then in the belly of the rover, this is where we mount our payloads essentially. Here it's not represented, but normally you would have a multi-layer installation going around the rover here to keep the payload warm and it's actually the bottom of the belly of the rover warm. And our current rover also has a solar panel, vertical solar panel here. It was shown in the illustration before. It's not showing here, unfortunately, but yeah, all the avionics, printed circuit board, batteries goes in that little compartment here. And you mentioned, yes, we need to be extremely careful about how we manage the temperature of our batteries. The battery technology we use is a lithium-ion battery, and as you know, they're pretty sensitive to cold temperature, for charging the batteries. And the discharge temperature is also pretty narrow, right? So we need to keep between 0 Celsius and I believe 60 degrees Celsius as operating range throughout the mission. So We have heaters inside the rover. We have heaters a little bit everywhere. We have temperature sensors a little bit everywhere as well. So during the flight, during the transit, and during the mission, actually, we control the temperature, make sure we keep storage or operational temperature at all time. Yeah, and couple specs here. We offer some data storage as well. You can imagine the payload will generate some data that we will need to transmit at some point. So the rover provides some storage space as well here. And here you can see prototype of wheels we have been working on. So yeah. You cannot really see here, but the rover has two cameras, one on the front and one on the back. This is so we can drive in both direction symmetrically. And we use skid steering. We don't have the wheels are not moving essentially. It's just rotating them at different speed will let us generate different type of trajectory. Yeah.
Two questions here. One of them is, it seems like the data rate for Mars to Earth communication is tens of kilobit per second. From what I'm seeing here, it's similar for Moon, but shouldn't the Moon be much higher because it's closer? And second, have people like streamed the camera data from these rovers directly to the Earth?
Good question. The bandwidth we can get is the lander, I believe, is definitely more than 10 kilobits per second, but it's not like your Wi-Fi network. It's not megabits per second. It's in the order of magnitude of a couple hundred kilobits per second, I would say, in best case scenario. So yes, we could stream video, but they would be off. There won't be live video essentially. We would record the video, store it, and upload it slowly to the surface. And actually, that bring a good design point as well. We need to be extremely careful of what type of data we need to relay to Earth. We cannot upload. We need to be careful about the size of the image we upload. For instance, we need to compress them, make sure they can be. If we lose packets during the flight, we need to make sure that we can reconstruct the image regardless of that. So there is a lot of configuration to make as far as how we send that data safely and how to make sure that we keep getting data even if it's partially corrupted or missing, some bits and pieces are missing. So yeah, so it's all about designing the right protocol, making sure we have robust software implementation. So typically the way you drive a rover on the surface of the moon, you would probably take a picture, you look at where you are, you program your next command, your next driving command, say, hey, okay, I want to explore that rock, and you send a couple driving commands, your rover will drive there. It executes his driving command, probably send you some telemetry data, as far as, hey, everything is good, I'm moving forward, everything is fine, no problem with my sensor. And once it's there, just re-upload a new image, say, hey, I'm here, I'm waiting for my next command. That's typically the workflow you would get. And that's pretty much what Mars as well, rovers do as well, especially Mars has way more latencies at the moon. I think it's just the moon. I think we have 5 seconds, or some back and full.
The couple of other questions. Is there a specific frequency band which is used for this communication? And if so, is that regulated by NASA or FCC or someone else?
We use NASA equipment to relay the data. I don't know how much I can share with you, but we use their infrastructure to relay the data essentially. So I don't know the frequency they use. I think it's unique enough, so it cannot be hijacked by other or intercepted by other people, because one, I think you need to have the right dish that is gigantic, and two, you need to have the right protocol to communicate with it, and three, you need to be at the right time at the right moment to look at the communication. So there is a lot of uniqueness in the telecommunication protocol that is being used. Unfortunately, I'm not working directly on that, so I cannot comment too much, but yeah, pretty unique. It involved pretty big dishes. Yep.
Sounds good.
And between our rover and the lander, we use a pretty much a Wi-Fi-like protocol, essentially, to communicate with it between our lander and rover. Yeah, and there is a lot of interest, as you mentioned before, to develop other telecommunication infrastructure, for long-term presence. Here, you mentioned before the Nokia deal, but yeah, NASA is also very interested in supporting that rover and human telecommunication on the surface of the moon. So yeah, maybe one day we'll be able to send a selfie and astronaut using the 4G network or whatever. So, maybe. This is we have. If you are curious, actually, if you go on our website, if you want to fly a payload with us, you can download. There is some PDFs you can download there, and essentially we will give you a little bit more insight of what it takes to fly a payload to the moon. So you will see there is all type of requirements, pretty easy to read, and it will give you a good idea of how a mission look like. And yeah, so it's on our website.
I think we have a bunch of questions. This is great. Thanks a lot for sharing these things. I had to go back a lot because there's so many questions people are asking. So, okay, so first one is from Alex, which is the dust on the moon. You mentioned that it causes issues. So given that, how long does the rovers expect it to last, and how do you simulate that on Earth as well?
Great question. Yes, so the lunar dust is creating problems for instance, for thermal management, because if it covers your radiator, they will decrease the performance of your radiator quite drastically, actually, and you don't need much. So we are looking into a couple of things. We are looking at passive way to mitigate the dust. It could be just using fenders or those type of mechanical feature and are designed to try to limit where the dust could ingress, essentially. We're also looking at active ways to mitigate the dust, by maybe pushing it out. It's in our box. We're studying that. How do we simulate that? Good question. We have some test beds that have actual lunar simulants, and their properties are close in some respect to what we would expect on the moon. Some simulants are designed really to behave like electrostatically the same way that what we would expect on the moon. So what we do, actually, we have some test equipment that measure the susceptibility of some material to stick to a surface. So that's how we test our material, and to verify that picking material A versus B is better, or by doing some compound testing of that material. But yeah, dust is definitely big problem on the lunar surface. Thankfully, as opposed to what, I don't know if you recall, but during Apollo 16, for instance, you have the Jeep, or not the Jeep, but the lunar rover vehicle It looks like a Jeep, but that was moving dust everywhere because they were driving super fast, so you have the dust flying everywhere, sticking everywhere. So they had a lot of trouble controlling that. Thankfully, with our rover, we go at a much lower speed and we don't expect to have that much problem, but it's to be definitely verified once we're there.
So another question is from Laurel, which is about the size of your rover and lander. What determines the size? I mean, right now it's like around 10 to 30 centimeters. Is there a need for going smaller? Do you see like micro rovers, or like how did you basically say that's the right size to target?
That's an excellent question. We have some use cases where so because it's very expensive to fly something to the moon. The market need we're trying to address is to reduce the size as much as possible of the rover, reduce the footprint of the mobility structure as much as possible, just so essentially you have that payload that the science community design. We try to reduce the overhead, of bringing a payload on the surface of the moon as much as possible, and that was driving the size of the rover essentially. A lot of payloads we saw were quite small, or most of them are actually small, and you don't want a big rover to carry them around. So that was a motivation to have a small rover that essentially could go in, pits, and it would be affordable for our payload customer to fly to the moon. So affordability is one thing we try to advertise, in a component selection, design, and where we try to simplify a lot of things that to reduce the mass and the complexity of the system as much as possible. That was a driving factor. I think that's how we ended up with that CubeSat approach type of things.
So the next question is from Hannah, who was asking the question of for the payload carrier like the Peregrine, is the pre-mission and post-mission checkout process for vehicle health entirely autonomous, or is it something done manually?
Yes, there is a lot of checking. So once we land, yes, we have a checkout phase to make sure that all the payloads, once we land on the moon, are good to go. So there is a phase where, yes, we will do a self-check of the lander. Yeah, and every payload will be able to every payload customer will be able to check, hey, is my payload still alive? Did it make the flight? Yep, we do, and also during the flight, we do some periodic checking to verify that the spacecraft is working as expected.
Cool. Jack has a question on: do you use ROS as your operating platform?
I can tell you, not for the lander, maybe for our rovers.
I think I had two questions from the two different Alexas, basically about the business case for this. Like, are you thinking about considering opportunities for private companies like SpaceX? And also, like, what do you think on the long term the business side of lunar exploration would look like? Do you think that the commercial interest would outpace government interest anytime soon?
That's a good question. So I will speak to my experience. I'm definitely not in the business development side of the company. But from what I know, there is a lot of interest from NASA to contract out designs. So essentially, NASA will create solicitation and will do calls that to essentially push companies like us and SpaceX and others to come up with creative solution and more cost-effective solution. So NASA actually can focus more on the science and less on the logistic to send their scientific instrument to the moon. So I think that's the motivation that why NASA is relying on the private partners to one, get the best price because of the competition, and two, just think outside of the box essentially, because they're, people have more different backgrounds, from private companies that maybe NASA, for instance. I don't know for sure, but it gives different perspective to NASA, and I think that's that. I think the NASA is evaluating to do more and more contracting like that in the future, at least definitely for Artemis program.
So we have another question from Amy, which is, how do you fit the rover into the containers that store and release CubeSats? How does that work with the lander since the CubeSats do not land on the surface?
Oh, that's a good question. Yeah, we have a pretty cool deployment system, actually. I don't know how much I can share, but we have our rover installed on the lower deck, typically of our lander, and we use hold-on release mechanism. Essentially, they are little single use trigger that once they are triggered, they will open a bracket, for instance, and or rover drop on the surface. And because the height where we get dropped is about, I would say it's about 4 feet or something like that, 5 feet. At 1/6 of the gravity, the drop at the end is not that bad. And we do testing actually here on Earth at a lower height to verify that our rover can survive that drop. Yeah.
So one of the slides you mentioned said that the power you're giving for the payload is around 0.5 watts per kilogram. If I remember, that seems like a pretty small amount of power. I mean, even if I created like a PCB, let's say let's say I can create something for a gram.
Yeah.
But the amount of power you're talking about is like really small. So what kind of payloads are people doing right now? That's actually from a research perspective, that's great because that's the kind of a power which we like to work at. But like, I'm just wondering from a practical perspective today, what are people deploying in terms of payloads?
That's a great question. So that number is actually the average power. So if you want to use more, you can use more. But what you be mindful is, the more power you use, the more heat you will generate, and that's more heat to manage and to dissipate on the surface of the moon. So what we need to look when we need to take a more closely for those high power payloads is their duty cycle, essentially. So if you want to use 10 watts, it's fine. The system can support that, no problem at all, or 20 watts, whatever. it's fine. It's just how long you need those, otherwise the rover could overheat, or we need to put some extra design consideration to make sure that we can manage the temperature more carefully. So that's why. It's a baseline, I would say, a baseline number. Then, yeah.
There's a lot of duty cycling, is what you're saying.
Yeah.
Cool. And just as a last question before we have 1 more minute before we can let you go, actually, maybe I'll ask the question of the student as Jan, which is someone working in the space industry. Are there any policy changes we think you should implement to be better stewards of the moon?
I don't know. We do have some policy changes. I don't know. We do have some loitering policies where we cannot, spread garbage on the surface of the moon, obviously. But I don't know.
One last question which I wanted to ask you, which is, do you have any channels for like researchers and universities to deploy prototypes for like various sensors or various communication systems? Is there any kind of a way in which you as a company work with researchers to do this kind of deployments?
Yeah. Absolutely. Yeah. NASA has a specific, contract with universities to develop some sensors or new technology. Absolutely. And and actually, Josh and I, we were working on something together few weeks, a couple months ago. So yeah, there is definitely opportunities for university to participate to those efforts. Yeah,
Cool.
it's great. It's wonderful. I love working with you guys, with universities. It's awesome.
Sweet. So thank you so much, Cedric. Really
Absolutely.
appreciate you taking the time during your staycation and talking to us. Have a nice and relaxing staycation.
Perfect. Thank you very much. It was a pleasure to talk to you.